So, therefore, we go back to this particular diagram. This is the simplest of the diagrams where we show only the translational periodicity. So, that means to say that the types of 2-dimensional lattices we can have depends upon the nature of what kind of symmetry elements we can associate with these objects. So, if there is a translational periodicity, there is a 2-dimensional lattice. There is a 2-dimensional lattice which has a 2-fold symmetry. There is a 2-dimensional lattice which has a 3-fold symmetry, and so on. So, how can we go further, and in what way we relate one object to the other in terms of the symmetry? You see, we are talking about only translation symmetry. That means that the object can be 360-degree rotated, that is a 1-fold symmetry. We have talked about the 2-fold symmetry, presence of 2-fold symmetry. We have talked about 3-fold symmetry. We also talked about the 6-fold symmetry, and similarly we can talk about the so called 4-fold symmetry. One of the conditions which we have always been telling very quietly is that these diagrams which are drawn by Esher have a close packing, and if we have a 5-fold symmetry object and want to do a close packing, we will show later on that it is not going to be possible, because we will have some holes left in this 5-fold symmetry packaging. And because of the fact that 5-fold symmetry packaging will have holes, it will not satisfy the conditions that we need for defining a 2-dimensional lattice, and therefore the number of rotation axes get restricted to 1, 2, 3, 4 and 6. We will mathematically prove in a later class that it is only possible to have 1, 2, 3, 4 and 6, and this restriction comes because of the presence of the translational periodicity which is in the solid state. So, the presence of the symmetry 1, 2, 3, 4 and 6 is only there in case of solid materials, and particularly in case of crystalline solids. So, that way the amount of effort we have to spend in understanding the symmetry of objects get reduced because of the presence of the translational periodicity. Since there is translational periodicity, we do not get 5-fold symmetry operations, for example. Similarly, 7, 8, 9 and so on are also not possible. We are going to prove it mathematically in the next coming class, maybe in the next class or so. But for our current understanding, we need to note the fact that once we require close packing, once we have translational periodicity and we have the presence of the symmetry elements, we can now appreciate the Escher's diagram in terms of all these presence of symmetry elements, and replace these imaginary abstract objects by molecules. Then we can have these molecules also following the same symmetry operations. So, we can have molecules packing themselves in a 2-fold symmetry situation. We can also have the molecules packing together in a 3-fold symmetry situation and so on. One of the things we also have to notice in this particular case is the definition of what we called as A prime and B prime. See, here we called this as A prime and B prime, and we defined this so called block and we called it as a unit cell, if you recollect that part which we did in the previous class, half an hour class. So, the angle between these two is 90 degrees. Now, this therefore is a type of a lattice where the lattice points are located in these positions, and we have a 90-degree angle between these two. It is not necessary that A prime should be equal to B prime. See, if A prime is equal to B prime, you will get a square. If A prime is not equal to B prime, you will get a rectangle. So, the presence of a square and a rectangle can sort of generate this particular motif, depending upon whether A prime is equal to B prime or A prime is not equal to B prime. Now, these two units which we have defined in this red blocking are referred to as lattices, and these are referred to as plane lattices. So, we have a square lattice and we also have a rectangular lattice. If we go to the next diagram where we had this threefold symmetry, you see that this, if you take this threefold point and join it to that threefold point and join this to this threefold point and join it to the next threefold point, something like this, you see now that you get a unit which is now having a different than 90-degree angle. So, this will now define a different kind of a plane lattice. Okay. So, we will see as we go along how many plane lattices are possible. What is very interesting is to note the fact that in solids, because of the translational periodicity, restrictions come to the in terms of the shape of the so called unit cell which we are going to define. So, we can define two types of unit cells now, three types of unit cells, when A is equal to B and alpha is equal to 90 degrees, A not equal to B, alpha is 90 degrees, and here you can find out what should be this angle. I want you to think about what could be this angle. If this angle is 60 degrees or 120 degrees, both are possible for this particular unit, and therefore you will get a threefold as well as a sixfold rotation that can be describing this particular lattice. So, we will come back to this translation periodicity again, and in this particular case, as we have already noticed, there is close packing and also there is translational periodicity. So, this comes because of the fact that this object will repeat itself at that object, and that object will repeat itself in this object and so on. So, we also defined the some kind of a unit cell. We will expand on that a little more before we go and understand the symbols that we are going to use, because the symbols that we are going to use that will become a very critical issue. The types of symbols which we are going to use are listed here. The reason why I have given this particular slide about which I will refer again later on is to tell you the representation of symmetry. For example, if you have a symmetry like 1 bar, you represent it by a closed circle. So, if there is a two-dimensional lattice and there is a 1 bar symmetry in that one, that is the inversion symmetry, then you represent the point at which the inversion is occurring by showing a small little open circle to represent where exactly is this particular inversion center located. So, if you now consider the two-dimensional object which has an inversion center, then that particular two-dimensional object will have not just the inversion center indicated, it will also have translational periodicity. So, if it has translational periodicity, it will have a plane lattice. If it has a plane lattice, then it will have either a no fold symmetry or a 360 degree rotation one fold, or two fold, or three fold, or four fold, or six fold. It will not be having any other symmetry elements which will come in. We are going to mathematically do that in the next class, but at this particular point we will see what are the symbols which are universally used in literature, because this is what will be used in crystallography and we are going to use it repeatedly as we go through the course. These are the symbols. For example, for the two fold we have this representation, and for the three fold we represent it that way. This is as long as the axes are normal to the plane of the projection. So, we have this is the two-dimensional projection and we are looking at the normal to the projection. That means, we are looking down into this screen, and when we do that, these are the representations of the inversion symmetry. If there is no symmetry, there is no representation, which is 1 of course, the 360 rotation. There is no need to represent a 360 degree rotation. So, we do not have any representation. It essentially tells you that the object is onto itself. So, the object is onto itself in 1 bar, it is onto itself in 2 fold, it is onto itself in 3 fold, and so on. There is also additional symbols which we will describe in more detail as we go along, and these symbols represent the so called screw motion. If you go back to the previous class, you will see that we talked about the objects of direct congruence. The objects of direct congruence can have these kind of symmetry elements. This sort of symmetry elements which are referred to as 2 1, 3 1, 3 2, 4 1, 4 2, etc. These are called the screw axis. What 2 1 represents is interesting. It represents the presence of a two-fold symmetry, and it is not just the presence of a two-fold symmetry, but there is a translation associated with the two-fold symmetry of 1/2 the unit cell. Let me explain again that when you say 2 1 axis, you have the presence of a two-fold symmetry, and then there is a translation. The two-fold symmetry alone is not finishing the operation. So, the object now will see the two-fold, and it will also see the half translation along the unit cell. It is something like, you know, you driving a screw through the wall. When you send a screw through the wall, what you do is a rotation which you give on the screwdriver. So, there is a screw fitting into the wall, you give a rotation in this direction. When you do this rotation, the forward point of the screw will go inwards. If you do the opposite rotation, the forward point of the screw will come back. And it is designed in such a way, this 2 1 screw means that when we rotate it by 180 degrees, the advance that is made is equivalent of half the unit cell in that particular direction. And that is therefore, it is effectively 1 divided by 2. So, this is referred to as the screw. We will be seeing examples in more detail for these kind of operations. Similarly, we have the 3 bar, 4 bar and 6 bar. These are 3-fold rotation with inversion centers, 4-fold rotations with inversion centers, and so on. The representation of axes which are 2 and 2 1 parallel to the plane of projection, that means a 2-fold or a 2 1 screw axis which are parallel to the plane of projection. So, this is parallel to this plane, then we represent them like this. This is the 2-fold representation, this is the 2 1 representation, that is the 2 1 representation. So, therefore, all the possible symmetry elements which occur in 2 dimensions and eventually the 3-dimensional issue will come up in these representations. So, these representation, for example, of a mirror is essentially telling us that the axis parallel to or inclined to the plane of projection. So, that means that there is a mirror plane which is like this, passing through this plane. There is a mirror plane which goes through like this. If it is perpendicular to that, it is shown in the right side. So, if you study this table carefully, these are the various symbols which will appear in the description of crystal structures and also these so called point groups and space groups which we will describe in the coming classes. You will see these symmetry elements displayed on the side or on the object itself. These are known as symmetry diagrams, and when we talk about symmetry diagrams, we will read these into more detail. At this moment, I showed essentially to tell you that we will be using some of these symbols for the next part of some of our understanding of how to locate the symmetry elements on a 2-dimensional object. And that is why I have given this table. This table will repeat again during the course, where we will go individually and explain the performance of each of these rotation operations with respect to a point in our molecule or material or the object in general. As you should always remember that even though we talked about objects and similarity of objects, once we refer to the 3-dimensional space and associate the symmetry with that 3-dimensional space, it is always the fact that the 3-dimensional space will have that symmetry. Suppose there is a 2-fold rotation associated with the object which we have described, like the flying cat in our previous example, then the entire space has 2-fold symmetry. Whether there is a cat or not, the entire space has 2-fold symmetry, and therefore, the space now itself is governed by the presence of the 2-fold symmetry. Anything you place in any point in this 2-dimension space, therefore, will follow the 2-fold rotation. So, if you have an object coming at a particular point, that point will now undergo a 180-degree rotation to represent the 2-fold. The only important thing is the direction of the axis, and that is why this table is shown here. The direction of the axis, if it is perpendicular to the plane, is represented this way. If it is along the plane, it is represented that way. So, it is perpendicular to the plane, it is represented this way, and if it is along the plane, it is represented that way. So, these are representations which you will see associated with the so called space group diagrams, and eventually this will be the one which will describe the nature of the object inside the unit cell and how these objects repeat themselves using the symmetry concept. So, that is what we will study towards the next few classes. We will get an understanding of how this all happens. Okay. Now, let us go further. Here is an example of presence of a two-fold rotation axis which is now perpendicular to the plane. So, in the plane, this is the Escher's diagram again. You see some lizards here, white and black lizards. This is very beautiful representation, even though Escher himself was not a crystallographer. All of crystallography is there in Escher's diagram. So, this is very beautiful if we look at these diagrams and try to understand the concepts, and that is why I bring in this issue of Escher's pictures. For example, here if you take this white lizard and take this white lizard, these two white lizards are related to each other with respect to this particular point where the noses are intersecting, for example, and they have, I have marked a two-fold symmetry at this particular position. That means any point in this object will have an equivalent point in that object. Please note the word equivalent. So, if you take a point x, y, z here, if you take a point x, y, z which now represents the two-fold axis, see this entire two-dimensional space now is filled with two-fold axis, and I have given a representation of a unit cell. This unit cell now is like a frame. I can move this unit cell. This is this is showing, this is let us say A, the distance at which this translational periodicity repeats itself. That means these two motifs repeat again in these two motifs, and the black ones, for example, and the white ones again repeat here. So, this is the so called unit cell which now repeats itself in both directions to generate the two-dimensional lattice. Now, we have identified the position of the two-fold screw axis here, the two-fold axis here, not screw, sorry, two-fold axis here. This is a two-dimensional object. And then we also see that in addition, once we have identified the two-fold symmetry here, automatically there is a two-fold symmetry comes up there, which is due to the unit translation, and the two-fold symmetry comes here due to unit translation. Two-fold symmetry comes here due to unit translation. So, if you take any point in space x, y, z in the two-dimensional space, it could be here, 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 anywhere. It will take the object, that particular point x, y, z will use the rotation axis. Now, the rotation axis is perpendicular. So, everywhere you can think of two-fold rotations coming in this space. So, any point here will now undergo the two-fold rotation. So, mathematically x, y, z now will go to minus of x, minus of y, z. In this particular case, we are looking at the x, y projection. That means this is now 0 and this is A and that is B, let us say, or in fact we should write here x and this is y, and the unit cell vector in this direction. I am using the word vector. I am assuming that there is a basic knowledge of vector analysis which all of you have undergone in your mathematics classes around the standard 12. So, I am assuming that you have an idea of what a vector is. Just to recollect or recount your idea of a vector is one in which we represent not only the magnitude, but it will also have a direction. So, if we take this point as 0 and then we move in this particular direction like that and reach this point, which is now again the end of the unit cell, and I will call this as A, and this is along the x direction, and along the y direction I will call this as B. So, this representation we will not call this A here, we will not call that B here, because A and B now represent the dimensions of the unit cell, and these x and y represent the directions. So, you see that any point in space, something like this point, which is let us say x, y, z. Now, we will see the two-fold symmetry. It will see the two-fold symmetry, let us say at this point. This is at 0, 0, 0 of our unit cell. Then if we see this two-fold symmetry, x, y, z will now generate a minus x minus y z. where do you think it will come? It will now undergo this two-fold rotation. So, it will go like that and come somewhere there. Okay. So, there will be a two-fold rotation about that particular point. What is very interesting about this lattice is that once we have the lattice which is generated with respect to A and B as the unit cell dimensions, two-fold symmetries exist at every one of these points, in every point in the two dimensional space, and certainly at these points where you have the two-fold rotation in this particular example. And therefore, it will also see the presence of two-fold at this point. These are additional two-fold symmetries, they come due to the translational periodicity. What you see here is that this center of symmetry, this two-fold symmetry is with respect to the presence of the intersection of the nose of each one of these lizards, whereas here you see that it is at the intersection of the two legs of the lizard. So, the object is so oriented that you will have a presence of additional symmetries which appear. So, whatever symmetry appears here at half the distance along A and half the distance along B, an additional symmetry exists. Like for example, you have this point and this is at 0 0 0, this is at 0 0 0 because we have taken this as the origin. Then at A we get a two-fold. So, this is at one unit translation. Then again one more unit translation in this direction will give you the next A and so on. In addition to the presence of this two-fold rotation, because of the fact that we have a two-fold here and a two-fold here, an additional two-fold will develop at this point. So, the objects therefore which arrange themselves with the two-fold symmetry in this particular motif has to sort of remember. For example, this lizard now cannot move its leg away from here. It has to keep itself the leg in that position in order to get the two-fold symmetry. Otherwise, it will not fit into this motif. So, if Escher had made a mistake and shown this leg as a different leg, then it will not be a closed packed filling motif. Therefore, the restriction comes now on the object. So, the object now therefore must have the two legs intersecting at this particular point if it has to keep that shape, and it is very interesting that lizards can do that kind of an operation, and therefore, we can fit the lizards into this two-dimensional motif. So, molecules when they fit in, they also have to remember the fact that apart from the presence of the two-fold symmetry, they also have the invoking of the two-fold symmetry at this point and again at half this distance along A, half this distance along B, and also half of A, half of B, which is a different two-fold symmetry. That is why I have shown it in different colors. The ones at the ends I have shown by blue, the ones in the middle at half distance is shown by red, and the one in the very middle I have shown by green. We will see the significance of these when we actually look into the way in which molecules pack when we discuss the space groups, and the presence of the additional symmetries which appear because of the fact that we have a lattice, and the lattice has to obey certain rules which we are going to formulate as we go along. Right now we are looking only at the symmetries that are possible with respect to this motif. The presence of additional symmetries is a crucial thing, because the presence of additional symmetry will bring in the issue of defining this two-fold axis in the same way. That means, if you have an xyz and an minus x minus y minus z, this point will now also see this two-fold symmetry, and therefore, this point will now go over there with a 180 degree rotation, something like this. It will rotate by 180 degrees and go there, and therefore, we will have this equivalence of x bar y bar z. So, in this particular two dimension space, therefore, we define x bar y bar z bar, x bar y bar z rather, as the operation which takes the object onto itself using the two-fold axis, the presence of the two-fold axis in this motif given the x y z directions. Suppose there is a two-fold axis which is in the x direction, then we see that the two-fold axis, if it is associated with the x direction, then your x y z will then go, if this is the direction x direction and we look at now the y z plane, then x y z will go over to what? To x y z will now become x y bar z bar. So, it will go to x minus y minus z, and it is the way I pronounced it. We always use this x y bar z bar, and in crystallographic notation we will represent that as x y bar z bar. So, we write a bar over y and z and pronounce it as bar. So, if the axis about which, so suppose x is coming towards out of the plane of this diagram, then the x y z will go to x minus y minus z, and that represents the two-fold symmetry along the x direction. Similarly, along the y direction we can define the two-fold symmetry. We will see very interesting observations which come out of the fact that we can have two-dimensional two-fold axes intersecting with each other and so on. Right now we are discussing only the presence of one two-fold axis in this diagram, and we will restrict ourselves to one two-fold axis. So, I think at this stage we come to the end of the second part of the talk. This is the second half hour. So, what I will do is I will conclude what we have done so far. What we have done so far is that we have looked at motifs, and we have looked at the possibility of arrangement in two dimensions, and we have looked at the arrangement in such a way that we identify the presence of symmetry elements, and we have taken one example of the presence of a two-fold axis, which is now generating the so called equivalent points. So, these are referred to as equivalent points. So, in a two-fold symmetry containing object, if there is a two-fold axis, the equivalent points are x y z, x bar, y bar, z, if z is the direction of the two-fold axis. In other words, if z coincides with the two-fold axis, as we have shown in this particular picture. I think that comes to the end of the second half of the talk. We will now go further and examine from this stage how we now can look at the other axes which can come up, other symmetry positions which can come up. Okay. So, I think we will stop here for today. Thank you.